This is Birhan. I recently graduated from University of Florence. Today I will share with you one of my projects entitled Ground Subsidence in the Dallol geothermal area, insight from InSAR observations. So Dallol is located in the northern part of the Afar Rift, which is within the East African Rift system. It's a zone of plate separation between Nubian, Somalian, and Arabian plates. It's also a place where we have a triple junction between main Ethiopian Rift, the Red Sea, and the Gulf of Aden. To the north, we have Danak Depression, where Dallol is also located. Danak Depression is bounded by the Danakil Forest from the east and Nubian Plate from the west. It's also a place of active magmatism and tectonism. It's narrowly elongated towards the northwest direction. It marks one of the lowest elevation on Earth. So Dallol is located in the northernmost part of this Danak Depression. It can be characterized by extensive evaporite deposition on the surface and some hydrothermal activities. And at the edge of this salt deposition, we also have some clastic and marine deposits. And to the west, we have the western boundary that is Precambrian succession. So these are some pictures taken from the center of Dallol and some areas in the south, Black Mountain, and one of the pools in the area called the Gadaale. So in general, we can see that we have extensive hydrothermal activities like hot springs, fumaroles, and some salt dissolution and salt mineralization activities. So previously, the area has been studied by InSAR technique. So the previous presenter already described about the InSAR. So it's a remote sensing technique that measures ground surface deformation by comparing radar signals captured at different times and detect if there is any movements of the ground within the given period of time. So previously, we have some MVSAT study in 2012. As you can see, we have concentric structures at the center of the Dallol, and this was caused by a diking event which happened just right south of Dallol. And then there was a period of quietness from 2004 to 2008. And in 2008, subsidence again happened at the center of Dallol, and yeah, as you can see it in the middle part of the image, and to the right, you can see it again, another subsidence InSAR image between 2014 to 21. However, the subsidence cause was not very clear. So in this study, I used InSAR analysis to describe the surface condition, the ground deformation condition in the area, and the causes of this subsidence. So I use Sentinel-1 data between 2014 to 23 and process InSAR image in the area from both ascending and descending image. So as you can see it, the ascending track to the left shows one anomalous zone that is center of Dallol, showing subsidence at the center of Dallol. However, due to some incoherence, we don't cover other parts. But in the descending track, you can see more than one subsidence structures that are concentric, corresponding to the Dallol area, Black Mountain, and Bubbling Pool. So these subsidence structures show different subsidence rates, where the maximum is at the center of Dallol, that is 35 millimeter per year. To the left here, we have a velocity profile along with the topographic profiles across the given ascending and descending signals. And to the right, we have a time series data as you can see it, time series on Dallol and on the Black Mountain in A and C shows a continuous range increase or continuous subsidence throughout the given period. Where in B and D we have detrended plots of this C and A. We detrend this data just to show if there are any fluctuations. And on top of that, we also compare these fluctuations with the given precipitation data in the area, which is represented by the bar graph in B and D. However, we don't see any comparison between the two. So in order to know what causes this deformation, we jointly invert the ascending and descending tracks of InSAR velocity maps. So in A and D, we have the observed image of the InSAR data and jointly inverted. And in the B and E, we have the models along with the surface projection of the seal models because we assumed Okada rectangular seal model to do the modeling. And then we have C and F, we have the residuals. So the extracted parameters from the inversion show that Dallol is subsiding from 1.5 kilometer deep. Black Mountain is subsiding from 1 kilometer depth, and Bubbling Pool is the shallowest one that is at 0.6 kilometer. So what causes this subsidence? First, we looked at on the surface, what we have on the surface corresponding to these three maximas. So on top of Dallol, like I showed before, we have high intense hydrothermal activities together with some salt dissolution and acidic activity. On the Black Mountain, we also have some hydrothermal activity, but we have extensive salt dissolution that are pouring out on the surface. These salt dissolutions are mainly secondary salt dissolutions. And on top of bubbling pool, we just have bubbling pool that is bubbling at a medium temperature. When we look at the subsurface distribution, this is a simple sketch to show how the subsurface distribution of the contracting sources looks like. So to the base, we have an intrusion that is defined by the 2004 InSAR event, but prior to that, magnetic and gravity surveys also define the presence of some intrusion at the center of Dallol. So InSAR modeling confirmed this intrusion is located at 2.4 kilometer. So we have this, and right on top of that, we have our seal model that is at 1.5 kilometers. And for Black Mountain and Bubbling Pool, we have at shallower depths, and they are connected by the transverse faults. So in order to know what we have at these depths, we see some geophysical data. For example, we have MT data that is magnetotelluric. This is magnetotelluric data at 1,000 meter. So if you see these slides, we can see concentric high resistivity structure between this Black Mountain and Bubbling Pool. So in geothermal environment, this high resistivity at depths is interpreted to be some boiling activity. And at Dallol, we can see that it's a kind of transition between this high resistive to conductive region. And the slice of MT at 1.5 kilometers shows completely within the high conductive zone, which is interpreted to be partial melt zone. And following this cross-section line, we can see a cross-section of this MT and the Bubbling Pool and Black Mountain and Dallol contracting sources distributed on the MT profile. So from this, we can conclude that the Dallol subsidence is caused by cooling of the magma, or the magma that is the top part of the previously defined intrusion. And on top of it, of course, we have hydrothermal circulation zone as depicted from the image. In Black Mountain and Bubbling Pool, since it's within the high resistive zone, we can interpret it as a hydrothermal area. So this subsidence in these two areas is potentially caused by hydrothermal depressurization. But on top of that, on Black Mountain, since we have extensive salt dissolution, this is also caused by salt dissolution. If we compare the depth of the Black Mountain and Bubbling Pool with the subsurface borehole data, they correspond to the potash bearing layer, where we have salt dissolution that are very susceptible to it. So the Black Mountain should also be caused by these salt dissolution processes. So in conclusion, this study confirmed the continuity of subsurface subsidence in Dallol, especially between 2014 and 23, where the deeper source is caused by magmatic pooling and the shallow sources are caused by hydrothermal activities and salt dissolution. And the study also shows that interaction between evaporite and fluids causes ground deformation, ground subsidence. It also confirms the presence of shallow magmatic processes along the East African rift system. And finally, the study shows the contribution of InSAR for geothermal exploration. So if you are interested in this study, since this paper is recently published, you can access it from GCubed. So thank you.
Thank you very much, Birhan, for a wonderful presentation on what is happening in the Dallol. So we'll open it up for questions. Birhan, maybe just to check again, the Dallol area is a very hot place and also most corrosive. How is it using ground-based monitoring in the area?
We use the InSAR, which is not ground-based.
Yep.
Yeah.
But if you are to combine, for example, the way we have the GNS stations and together with InSAR, would that still be okay? Or
I think it's okay. There are some geophysical surveys which have been done before, so it should be okay.
you mentioned also about the acidic. There was something about the acidic pool, or what did I get? Or acidic
Yes.
water? Just find out what is the range of the pH in the area.
I hardly remember the number, but it's super acidic.
Okay, so then it makes the InSAR technology much more useful.
Yes.
Okay, yeah. Any other questions from? There's a question from Derek.
Okay.
Thanks, Birhan. I'm asking, I know the work 'cause I was involved in it, but we have time for a question. You mentioned this cross-rift fault linking some of the structures. Maybe you can discuss a bit more about the evidence for that.
Yeah, well, the cross-rift structure between these, especially between these two, is defined from the surface view first. When we look at the Bubbling Pool, Black Mountain, and another, here we have our present this picture here. So if we look at the surface features here, we have some connections between these features. They are connected inside, but on top of these surface features, we have also magnetotelluric data confirming the presence of cross-rift structures right in this part. In addition to this, also the MT data confirm the presence of cross-rift structure on north of Dallol as well.